So hello everyone, good morning and welcome to the ACM Winter School. So today we are mostly focusing on the computer architecture. Today and tomorrow we are mostly focusing on computer architecture area. In this session, this is mostly related to processor data path, pipelining, branch prediction and dynamic instruction scheduling. And for this session our speaker is Govindarajan sir. So he received his BSc degree in mathematics from Madras University in 1981 and BE Electronics and Communication and PhD in Computer Science from ISC Bangalore in 1984 and 1989 respectively. Since 1995, he has been with the Supercomputer Education and Research Center and the Department of Computer Science Automation in ISC Bangalore. His research interests are in the area of high performance computing, compilation technique, and computer architecture. So with these statements, so now so Rajan sir, now you can give enlighten us with the in this area.
And
Sure.
I'll just add that Govind sir taught me architecture, so all I know about architecture is actually from him. And it
I,
was sort
I,
of a selfish motive that I sort of invited him for this because I wanted to sit for his lectures again. So I would really encourage all of you to just pay as much attention as you can. So it's a huge privilege to be able to listen to him talking about architecture. So sir, please, I mean, it's all your stage.
Thank you, Avnish, for the nice introduction, and thanks, Subhajit, for the additional remarks. I'm indeed honored to be here to give these lectures on processor architecture, specifically on processor data path and ILP architectures today, and then talk a little bit more about multi-cores tomorrow. Let me just get started with the overview of this talk. We're going to have a very quick introduction followed by discussing the processor data path. Then we will talk about how pipelining can be done in the processor data path. And then we will talk about important issues relating to branch prediction and how dynamic branch predictors are implemented. And finally, we will try to conclude our discussions with certain aspects of out of order issue and execution, which will set the path for Professor Madhu Mutyam to take over, where he will talk about superscalar architectures. So roughly, this is what we are planning to do in this 1.5 hours. Let me briefly get started with instruction set architecture, right? Instruction set architecture is essentially a description of the machine from the viewpoint of the programmer or compiler. It is actually the aspect what the compiler or the programmer would see from the machine, right? So this instruction set architecture essentially includes things relating to the set of instructions which are supported by the processor, the set of addressing modes supported by the processor, where addressing mode is nothing but the way in which you specify the operand for each of the instructions. And lastly, there is a small aspect which is the instruction format, which is needed by the processor to understand how the instruction has to be encoded. We will not spend too much time on the instruction format. Okay, now when we talk about instruction set architecture, right, there are two ways or two kinds of instruction set architecture. One is what is called the complex instruction set computers, in which the individual instructions are complex to perform, individual instructions can perform a complex task. As opposed to this, in the reduced instruction set computer, each instruction can perform only a simple task. So a complex task has to be performed using a collection of operations or collection of instructions. But the advantage of the reduced instruction set computer is that because each instruction is simple, it can be implemented in a very efficient way and perhaps with a faster clock and in a pipelined manner, so that the collection of instructions which is meant to accomplish the same task as a complex instruction can be accomplished rather quickly, even compared to the single complex instruction execution. Okay, we will not talk more about the CISC versus RISC debate. That's a separate topic. But our interest to talk about instruction set architecture is to understand how the processor execution happens. So from that perspective, if you want to look at the instruction set architecture, the first thing that we need to know are the different types of instructions that are there in the architecture. So these instructions could be, arithmetic and logic operations, where you perform add, subtract operations, or logical OR and AND operations, and so on. Or it could be data transfer operations such as loading value from the memory to a register or storing a value into the memory and so on. If it is a complex instruction set machine, it could also involve transferring data from one set of memory locations to another set of memory locations using a move instruction. Then of course we have the control transfer instructions which enable control transfers. For example, unconditional jump instructions or conditional branch instructions. And also you have things like function calls and returns, instructions for performing function calls and returns and so on. And lastly, the halt instruction is also a part of the instruction set. So each processor might support a set of instructions possibly from these different types or categories of instructions. What instruction exactly it supports, what variants it supports, depends on the processor. Okay, now the next thing that we want to talk about in the instruction set architecture is the addressing mode. Addressing mode is the way by which the instructions specify what are the operands of the instruction. Again, when you talk about the operands of the instructions, we talk about the source operands as well as the destination operand. Source operand is the place from where you take the input values, and destination is where you write the output value. Addressing mode corresponds to specifying these operands, and an operand can either be in a register, which is a general purpose register, or it could be in the memory, right? And of course, instructions can have either instructions can be in one of the two formats. It can either be in a 2-address format or it can be in a 3-address format. If it is in a 2-address format, typically it will have one operand which is both the source and destination. For example, in this subtract instruction, R2 could be both the source and destination operand, whereas the other operand A, which is a memory operand in this case, is a source operand. As opposed to this, in the 3-address format, you could have 3 operands. One of these operands is the destination operand, which is R1, and the other 2 are source operands like R2 and R3. Again, different processors have used different types of instruction formats. Some have used 2-address formats, some have used 3-address formats, and so on, right? Okay, now let's focus on the different addressing modes and what are the different types of addressing modes which are in general supported. And then when we talk about RISC architectures, what are the addressing modes that are supported in that? We will also take a particular case study of MIPS machine and then try to look at the instruction set architecture of the MIPS processor as well as the addressing modes which are supported in them. Okay, the first addressing mode and the most simplest addressing mode is the register direct addressing mode, in which the operand is available in a register. For example, again in the same instruction, add R1, R2, R3, there are 2 source operands R2 and R3 and 1 destination operand R2. So here the operand values are stored in the register, therefore those values are used, the addition is performed, and the result value is stored in the destination register. That's the meaning of this instruction. But the operands themselves are in the registers. As opposed to this, in the immediate addressing mode, the operand is specified as a part of the instruction. And this addressing mode is used for specifying small constant values. For example, if you want to add, let's say, a constant value 1 to a register value, then you could use this immediate addressing mode. Typically, you have cases where you want to add 1 or subtract 1 or add 4 or subtract 8 and so on. So those could be achieved using the immediate addressing mode, in which the operand value is actually specified as a part of the instruction. So this is embedded, or this is a part of the instruction format itself, instruction itself rather. The third type of addressing mode is what is called the register indirect addressing mode, where the operand is available in the memory, but the address of that memory location is specified by a register. In this case, R2 register has the address of the memory location which has to be accessed. So for example, if you assume that, right, R2 register contains a value 100 and the memory location 100 contains a value 10, then at the end of this operation, right, the contents of this memory location, which is 10 is moved to the R2 register or is copied to the R2 register, and you have the value of R2 register changed to 10, right? Now, a slightly more complex addressing mode is what is called the base displacement addressing mode, which is very similar to the register indirect addressing mode, except that the address of the memory location is specified by means of a register and a small constant. This small constant is actually added to the register value, and that gives the address of the memory location which has to be accessed. So, a computation of adding the value of R2 with this constant has to be performed, and this value is what is called the effective address of the memory location. Then the content of that memory location is then copied into the R2 register. So, in the same example, if you now look at it, right, instead of copying the value from memory location 10, we are going to copy the value from memory location 104, which is 4 bytes away from the first location. So, in this case, after the copy operation is performed, the value 35 is stored in the register, right. Typically, in a RISC machine, the base displacement addressing mode is used, and then the register direct and immediate addressing modes are used. The register indirect addressing mode is similar to the base displacement addressing mode, except that the displacement is always 0. Therefore, the effective address is actually whatever is the content of R2 register. Whereas in the case of a base displacement addressing mode, the effective address has to be calculated as an addition of the immediate value, which is in the part of the instruction, plus the register value. This immediate value can be positive or it can be negative. Okay, but it is always a small constant, and when I say small constant, in the case of MIPS machine, it's actually a 16-bit 2's complement number, which means that it could be from minus 32k to plus 32k. Okay, in addition to this, there are several other addressing modes which are typically supported in CISC machines. We will not talk in great detail about them, but let's just quickly look at them. The absolute addressing mode, in which the address of the memory operand, right, the address of the memory location is specified as a part of the instruction. This requires the instructions to be longer because the full address has to be specified as a part of the instruction. So, typically here the instructions would be 6 bytes or 8 bytes and so on, right. Then of course, you have the indexed addressing modes, in which the address is specified as a combination of 2 registers. Like in this case, it's the addition of R3 plus R4, which gives you the effective address of the memory location. Or it could be auto increment or auto decrement addressing mode, in which again the address of the operand is specified by a register, but in addition to accessing the memory location, the register or the pointer is either incremented or decremented, right. So, for example, if you have an array of memory locations, or an array of, if you have a array type of a variable, and these values are stored in successive memory locations, then to access them one after the other, typically one could use the auto increment addressing mode, because after you have accessed the first element, if you do an auto increment to that, then the register points to the next element and so on. So, typically auto increment and auto decrement addressing modes are used for that, right. Again, these addressing modes are supported only in the CISC architecture. In the RISC architecture, you don't have an auto increment or auto decrement addressing mode, but you have the index plus displacement addressing mode. After that, you either add or decrement the constant value to have the effect of auto decrement or auto increment. There is also another addressing mode called the PC relative addressing mode, in which the operand is specified with an offset from the current program counter value. So, this is typically used for storing constants. Okay, as I mentioned earlier, we will quickly talk about the MIPS instruction set architecture. The MIPS has 32 integer registers and 32 floating point registers. The integer registers, right, are numbered from R0 to R31, and R0 is will always have the value 0. It is always hardwired to 0, and R31 is used as the link register, which is used for implementing subroutine calls. In addition to these 32 registers, it also has two registers which are called high-low registers, which are used for multiply and divide operations. Because when you multiply two, so when you are multiplying two 32-bit numbers, the result will be a 64-bit number, and that is stored in the high-low register. Similarly, when you do the division, there is the quotient and the remainder. They will be stored in these two registers. And as I mentioned earlier, the MIPS architecture supports the immediate addressing mode and the register direct addressing modes, right? And it also supports the base displacement addressing mode. Since the MIPS architecture is a reduced instruction set architecture, arithmetic and logic instructions can only use the immediate and register direct addressing modes. Only load store instructions can have memory operands, and they are specified by the base displacement addressing modes. Conditional branches are implemented using the PC relative addressing mode, where the offset is specified with relevance to the current program counter value, and absolute jumps are specified as direct addressing mode or absolute addressing mode, where the address is specified as a part of the instruction. Okay, now let's quickly look at the different types of instructions that MIPS supports. As I mentioned earlier, MIPS is a RISC architecture, so it has the load store instructions. And the load store instructions again come in three varieties. You could load a byte, a half word, or a full word, and you could either load them as unsigned or signed, because if you're loading byte or a half word, they could be converted as an, they could remain as an integer, or they could remain as a unsigned value. That's essentially what it means. Let me put it that way. They also have this move operations, which is for moving values from the high-low registers to other registers. Then arithmetic instructions like add, subtract, multiply, divide, they always use integer operands or immediate operands. And as you can see here, right, there are different examples that I have given. The same thing also holds for logical operations and shift operations and so on. Lastly, we have control transfer instructions like conditional branch instructions, right? And examples of this is branch equals 0, branch not equal 0, and so on. And here the condition is specific, the condition operand, right, is specified by means of a register R2. So here you are checking the contents of R2, and if the condition is true, right, the branch happens with regard to the current program counter value with an offset of -16. So the program counter, right, is added with the value -16, and that will become the new program counter value if the condition is true. If the condition is false, it will simply remain as PC plus 4. One small detail here is that this offset is always with regard to PC plus 4 rather than PC, because as you will see later on, in the instruction fetch phase itself, the program counter would be incremented by 4, and therefore all the offsets are specified with regard to PC plus 4. Okay, I must also mention here that in the case of the MIPS instruction set architecture, every instruction is exactly 4 bytes long or 32 bits long, right? And therefore the program counter is always incremented by 4 to get to the next instruction. In MIPS, we also have the unconditional jump instructions like the jump instruction, where you can specify the absolute address where you have to jump as a part of the instruction itself, which is 26 bits, and the remaining 6 bits are specifying for the jump instruction. There is also a jump register instruction, which will actually use the register value as the jump location, and there are these jump and link instructions which are meant for implementing function calls. There is also a syscall instruction that is implemented in the MIPS MIPS architecture. Okay, let's just look at how the instructions are encoded in the case of the MIPS architecture. This is important for us to understand how instruction execution happens. There are 3 formats which are supported in the MIPS architecture. The first one is the R format or the register type format, in which case actually the 32-bit instruction contains 6 bits of opcode, and then there is a source register field, right? There are 2 source register fields and then 1 destination register field, and there is a 11-bit extra opcode information which is there, which is again split into two parts like shift amount and function. The shift amount is useful for logic instructions like logical shifting or logical logical shifting or arithmetic shifting, shift operations. Okay, and this is also a part of the opcode or instruction specification. So essentially, in an R type instruction or R format instruction, the two source operands, which are register operands, and one destination operand, which is a register operand again, are specified by means of three 5-bit fields, because there are 32 registers, right? Each register can be specified using 5 bits. There are 5 bits for the first source operand, 5 bits for the second source operand, and again 5 bits for the destination operand. And the rest are all opcodes or some shift amounts. Whereas the I-type format or the I format instruction consists of an opcode and then one source operand and one destination operand. It also has an immediate operand. For example, the branch instruction, the load instructions, etc., they use the I-type format. Even arithmetic instructions like add, subtract will use the I-type format, where one of the operands, one of the source operand is an immediate constant, right? That uses the immediate constant. And as I mentioned earlier, the immediate constant is a 16-bit value, which is specified as a part of the instruction. The J-type instruction is typically used for jump instructions, and that is meant for specifying the absolute address of the jump location. Okay. All right. Now let's just move on to the processor data path, so that we could understand how instruction execution happens in a pipeline, in a processor. Okay. So the instruction execution is split into a number of stages. We are going to see this to be split into 5 different stages. The first stage is the instruction fetch stage. And in the instruction fetch phase, the instruction is fetched from the memory, and the program counter contains the address of the instruction to be fetched. Therefore, you use the program counter and fetch that particular memory location, and that is the instruction that you want to execute, and that is saved in the instruction register. Immediately after that, the program counter is incremented by 4, so that that becomes the next program counter or the program counter for the next instruction. This is implemented in hardware using a simple ALU or an add function unit, or adder even you can say, right, which actually increments the program counter by 4, and that stores the value of the next program counter or the program counter for the next instruction. The program counter is used to index into the instruction memory, and the fetched data is essentially the instruction register, which is the instruction to be executed. The next stage in instruction execution, right, is the instruction decode phase and operand fetch phase. Remember that in the case of the MIPS architecture, the instructions, each instruction is exactly 32 bits, and the instructions have what is called the fixed format, right? It is either going to be in the R format, I format, or J format, and the most significant 6 bits are always the opcode. And the most significant 6 bits also specify whether the instruction is in the I format, R format, or the J format. So just by looking at the most significant 16 bits, you can decide what it is. But more importantly, what you do is that whether it is in the R format or in the I format, right, the source operands are specified exactly in the same location. Source registers are specified exactly in the same location. So what the processor does is that it takes the instruction, right, fetched in the previous phase, right, and then looks at the appropriate bits and then tries to index into the register files so that it can actually read the operands, right. So using the first source register, it will read one operand. Using the second source register, it will read another operand. So these two will be stored in 2 temporary registers A and B. At this point in time, the instruction decode phase may not even know whether the instruction is in the R format or I format or J format, right. It will simply assume that if it is in the R format, then the A register and B register will contain the 2 source operand. If it is in the immediate format, then the A register will contain 1 source operand, and then the other source operand is actually going to be the immediate operand because it is in the I format, in which case it will actually do a sign extension, right? It will actually do a sign extension of the 16-bit value to a 32-bit value and then store it in this temporary register called immediate. So all of this is done without completely decoding the instructions or without completely understanding whether it is an OR format instruction or an I format instruction, and without even knowing whether it's an arithmetic operation or a load store operation or a branch operation. Okay, so these are the two stages, first two stages in the instruction execution. Now let's see what happens in the next stage, which is the execute stage, where you have to understand what is the instruction to be performed. Is there a question? Yeah.
Sir, if there are three of them in the info in the IR, then it inputs three number of values in the register file, and one of them is taken by A and the other is taken by B. Sir, the remaining part will be extended to the immediate part with 32-bit.
When I said there are three operands, right? Two source operands and one destination operand. Correct? So the destination operand is the result. That is what the instruction is going to compute. So you don't worry about that. It could be two source operands, could be specified by two register files, or one specified by a register file and another specified by an immediate value. Right? Only in the case of a store instruction, which I will explain a little later, right? There are two source operands and one immediate constant. So one of the source operand is the value to be stored in the memory location. One of the other source operand is a part of the address to which the immediate constant is being added. So to put it in the right order, one source operand, right, in the case of a store instruction, is a part of the address that will be fetched and then loaded into the A register. The other source operand, which is the value to be written into the memory location, is going to be fetched from the register file and would be saved in the B register. The immediate constant is sign extended and would be saved in the immediate location. So the address, effective address, is calculated by adding A and immediate, as you will see later. Is that clear?
Yes, sir. Yes.
Okay, thank you. Right. So let's see what happens in the execute stage. So in the execute stage, we're going to understand what is the operation to be performed and what is the type of that instruction, whether it is using the OR format instruction or whether it is the I format instruction and so on. Let's first look at arithmetic instructions, right? If it is an arithmetic instruction and if it is in the OR format, then it is going to use two registers, and these two values are fetched in the operand fetch and decode, instruction decode and operand fetch phase in the A and B register. Therefore, you have to perform the instruction execution using the A and B registers, right? And then you have to perform the operation. So the A and B register are sent to the ALU by means of a multiplexer. Okay. So if you can appropriately select the inputs, the A will go to the ALU and the B will go to the ALU and the operation can be performed. If it is an arithmetic instruction with, let us say, an immediate constant, then A and immediate has to be selected and the arithmetic operation has to be performed. And the result of this arithmetic operation will be saved in the ALU out register. Okay. If it is a load store instruction, right, for the case of a load instruction, we have to compute the effective memory address, which is specified by means of the source operand or the source register plus the immediate constant. So here the source register value would be available in A and the immediate constant value would be available in immediate. So those two would be added and the effective memory address is calculated, and that value will be saved in the ALU out register. We still haven't performed the memory operation, which will be performed in the subsequent stage. Okay. So for the load store operation, right, the effective address calculation is what happens. I have given you the example of load. Store is very similar, right? For the conditional branch instructions, right, during the execute stage, the execute phase actually calculates the target location where the jump has to go to or where the branch has to go to. Again, as I mentioned earlier, the target location is nothing but the PC plus 4 value and then the immediate constant, right? The immediate constant is available over here. The PC plus 4 value which was computed in the instruction fetch phase is available in the NPC register, right? So that NPC is a temporary register. So from there you take the value, and then if you add the immediate constant to it, you will get, right, the target location of the program counter. But this target location value which is computed by the ALU will be saved in the ALU out register. In the case of a conditional branch instruction, there are two things that one has to do. One is to compute the target location where the branch has to go to, and another is to evaluate the condition of the branch instruction. The condition of the branch instruction is essentially specified as whether the value of A is equal to 0 or A is not equal to 0 or A is greater than 0 or less than 0 and so on and so forth, right? That is checked by means of a logic over here, and then the result of that condition is stored in the condition register, right? So this is exactly what happens in the EX phase. So in the EX stage, depending on whether it is an arithmetic operation or a load store operation or a branch operation, some computation is performed. For arithmetic operation, it is a computation that is to be performed. For the load instruction or store instruction, it is the effective address calculation. For the conditional branch instruction, it is the target address calculation that happens during the EX stage. Okay. Now, next, for the jump instruction, right? Jump instruction is an unconditional branch, and here the address of the location to which it has to be jumped to is specified as a part of the instruction, to which some zeros are padded, and then the most significant bits from the program counters are padded, right, to get the absolute location to where you have to jump to. And that value is stored into the program counter so that the next instruction will be from that location. Okay, now let's see what happens in the case of the Mem stage. The Mem stage is used only for load store instructions. Remember that during the EX phase, we have already calculated the effective memory address. So for the load instruction, we have to fetch that memory location and then store that value into the destination register. For that, what we do is that the effective address which is calculated and saved in the ALU out temporary register is used as the address, and the memory is accessed. Whatever is the value that you get, right, goes to the LMD register. Whereas in the case of the store instruction, right, this is the effective memory address, and to that address we have to store the value which was in the second source operand, which was fetched into the B register. So you essentially do a write into the memory in the case of a store instruction, and nothing really goes into the LMD register. Only for load instruction, the value which is fetched goes to the LMD register. For the store instruction, the whatever is the value which was in B is actually written into the memory location. Okay, all other instructions simply bypass this stage and directly go to the write back stage, which is the last stage. In the case of the write back stage, right, for arithmetic and logic operations, the result value which is computed is actually written into the destination register, right? The result value is available in the ALU out register, temporary register. So that value is stored back into the destination location. Whereas for the case of load store instructions, right, the value which is fetched from the memory which is in the LMD register, right, is actually written into the destination location. In the case of conditional branch instructions, the target address which was calculated in ALU out will be copied into the program counter if the condition is true. That means that the branch condition is true, then you have to jump to this new locations which was computed in ALU out, which is copied into the program counter. If the condition is false, then you just have to follow the next instruction, which is nothing but PC plus 4, which is available in NPC, right, and that is copied into the program counter. We already saw what happens in the case of jump instruction in the previous slide. and also we saw what happens in the case of a store instruction. So they don't go to the write back stage. Okay. So if you put all of these things together, this is how the processor data path looks like, right? We have the instruction fetch phase where the instruction is fetched and the program counter is incremented. We have the decode phase in which the instruction decode as well as operand fetch happens, and they happen in these temporary registers. Then during the execute phase for arithmetic and logic instructions, the operation is performed. For load store instruction, the effective address is calculated, and for conditional branch instructions, the target address is calculated as well as the conditions are calculated. In the memory stage, for load instruction, the value is loaded into the LMD register. For store instruction, the value is written into the memory location. And the write back stage, the result values are written into the destination location. In the case of conditional branch instructions, the values are written into the program counter so that the next instruction fetch can happen from that location. So if you put all of these things together, this is how you get the processor data path, right? Let me just add a few more quick details and then maybe pause for a few minutes to take questions. Okay. So if you put this processor data path again, then what we want to do is that each one of these stages we want to execute more or less in the same time. This is more important for pipelining the processors rather than just for implementing the processor data path. But if they all kind of execute, right, let's say more or less in the same amount of time, then we can call that as the processor cycle time. Right. For example, you know that your desktop processor operates at 2 gigahertz or 2.5 gigahertz and so on. That essentially means that each one of these stages is taking roughly 1 over 2 gigahertz of time, which is let's say 0.5 nanoseconds or 0.33 nanoseconds if it is a 3 gigahertz processor and so on. Right. So just to visualize this is really what happens. This is the processor clock cycle. And each one of these stages essentially completes in one processor clock cycle where you have a right, you have the clock being in the one state for half the time and being in the zero state for the other half the time. Right, that's essentially one clock cycle. Okay, so if you just think of your entire data path, then each one of the stages is being executed in one cycle, and therefore, if a particular instruction goes through all of these 5 stages, then it will take 5 cycles. If it goes through only 4 stages, it will take 4 cycles and so on. Okay, so if you assume that each one of these stages is going to take 1 cycle, then we can calculate what is called the cycles per instruction. On an average, how many cycles does the processor take for executing a program? That depends on how many cycles does the processor take for each type of instruction. We saw that for the case of arithmetic and logic instructions, it will go through all the stages except the memory stage. For the case of load instructions, it will go through all the 5 stages. For store instructions, it will go through all the stages except the write back stage and so on. Right? So we can say that the arithmetic instruction takes 4 cycles, the store instructions take 4 cycles, load instructions take 5 cycles and so on and so forth. Then if my program contains, let's say 40% of the instructions are arithmetic instructions, right? 10% of the instructions are store instructions, 20% of the instructions are conditional branch instructions and so on, then I can take the weighted average of the time it takes for each of these instructions, and that gives me my cycles per instruction. That means that in a program which has this 40% of the instructions as arithmetic instructions, 10% as store instructions, 20% as conditional instructions and so on, then it will take on an average 4.1 cycle to execute each one of those instructions. And then if my processor is operating in a 2 gigahertz clock cycle, then each one of this cycle is 0.5 nanoseconds. So that is 4.1 multiplied by 0.5 would be the time it takes to execute each instruction, right? And the execution time of my entire program is basically the cycles per instruction multiplied by cycle time multiplied by the dynamic instruction count. And here we insist on the fact that it is a dynamic instruction count because it's not just the number of instructions in your program. For example, if you have a loop which iterates 1000 times and that loop itself contains 10 instructions, then all these 10 instructions are going to be executed 1000 times each. So you will have essentially 10,000 instructions. Similarly, if you have a conditional branch instructions, right, then some of the instructions are going to be skipped. So here when you talk about the instruction count, you always talk about the dynamic instruction count and not the static instruction count in the program. Okay, maybe this is a good place to have a small pause, and then we will try to take some questions if you have any on the processor data path alone. Any questions? I'm sure all of you have seen these things in your undergraduate courses, and this is just only a quick recall of what you have seen there. So if you have any questions, please unmute and ask. Otherwise, we will move forward. Okay, so let's just go forward, and then again after another 20 minutes or so, take a few more minutes for question answers. Now let's look at pipelining, right? So up to now, what we have seen are the different stages of the processors, right? Pipelining essentially tries to pipeline each one of these stages in such a way that the throughput of instruction execution, right, is improved. So again, you just think of these 5 stages of the pipeline. One way is that you start the execution of the ith instruction, complete all its stages before you can start the I+1th instruction. That's normally what you do in a non-pipelined execution. Whereas in a pipelined execution, what you do is that as soon as the ith instruction completes its instruction fetch and moves to the instruction decode stage, the I+1th instruction, right, it can actually get into the instruction fetch stage. And similarly, when the I+1 completes its instruction fetch, the I+2 can be fetched, and so on. And what happens, the ith instruction, is that by that time the ith instruction would have finished the instruction decode stage and it will go to the execute stage, and so on. So if you keep actually fetching instruction every cycle and moving the previous instructions from its current stage to the next stage and so on, then what happens is that after initially the pipeline is filled, which takes about 5 cycles, in every one of the cycles you will actually get one instruction completed, right? So even though each instruction takes 5 cycles to execute, right, the throughput is improved, or the instructions per cycle is improved, because if it is an ideal pipeline, then what happens is that after each cycle you will have one instruction completed, because you didn't wait for the first instruction's execution to be fully completely over before you could fetch the next instruction. You started the fetching of the second instruction or the I+1th instruction as soon as the ith instruction fetch is over. Okay, so that's what we try to say, that the execution time of each instruction is still 5 cycles, but the throughput is what has been improved, and it has been changed to one instruction per cycle, right? Okay, now let's look at our processor data path and then see how the processor data path needs to be modified in order to accommodate pipelined execution of processors. Okay, so one important change that has happened is that since after the instruction fetch stage is over, in the next cycle we want to fetch the next instruction. Therefore, the program counter value which has been incremented in the instruction fetch phase has to be copied back into the program counter at the end of the same cycle, so that in the next cycle you can fetch the next instruction. Therefore, this processor data path has been moved over a little bit earlier over here. Okay, so that as soon as PC plus 4 is calculated, that value through this multiplexer goes back to the program counter. There is a little bit of complication here because of the conditional branch instructions, which we will discuss it a little bit later, right? course, the conditional branch instructions will actually compute the target location only during the EX stage, and that will be brought back along with the condition values, right, and that will be used to decide which one to take, but that we will discuss it a little bit later, right. In addition to this one change, right, the other change that you see is these long buffers that you see between these stages. Earlier, when the instruction is fetched into the instruction register, it remained available in the instruction register until all the stages were complete, right, because you are only fetching one instruction, going through all the stages of that instruction's execution till you complete. Whereas now that is not the case. As soon as the instruction finishes its instruction fetch, it goes to the decode stage, but around that time we start fetching the next instruction. So by the time the first instruction goes to the execute phase, right, the instruction register is being overwritten by the I+1th instruction, and by the time the ith instruction goes to the memory stage, right, the instruction register is being overwritten by the I+2nd instruction, and so on. We cannot afford to do this because we still have to complete the ith instruction. We need to know what the ith instruction is supposed to be, what its destination register is supposed to be, etc., etc., right. So what happens, is that the instruction register which was saved in the at the end of the instruction fetch phase is actually copied from there to the next stage in a buffer. So this buffer essentially consists of multiple registers, and some of these in between values that you need to remember for each of these instructions are actually copied over from one stage to the other stage, and they are being maintained. So for example, there will be one IR register in each of these buffers, and therefore when this IR register stores the ith instructions, right, ith instruction, this will be storing, this IR register will be storing the I+1th instruction. This IR register will be storing the I+2nd instruction, which is going through the execute stage. This will be storing the I+3rd instruction, which will be going through the decode phase, and so on and so on. Okay. So like that, there are a few other registers. Similarly, for your A and B registers, which we talked about, right, which you are going to use for, let's say, performing the arithmetic and logic operations or storing the value into the memory locations and so on. So the B register has to be copied from one stage to the other and so on. So there are this number of registers which have been added into the processor data path. The third thing is that each one of the stages should take exactly the same amount of time. That is when you will see things nicely overlapping like this. If some stage takes more time and some stage takes less time, then this overlap would not be nice, because when one is taking more time, right, the other one will try to get into that same stage. That's not possible. So in that case, what you do is that whichever stage which takes the longest amount of execution time, that determines the cycle time, and everybody operates at that speed, right. That's why I said earlier, it's important that each one of these stages roughly takes the same amount of time, because then you will actually call that as your cycle time. Okay. All right. So let's now talk about pipeline hazards. There are three types of hazards, right. Hazards happens because multiple instructions, they try to, hazards essentially talk about, why the pipeline does not remain like an ideal pipeline and being able to give you this throughput of one instruction every cycle, right. And there are three types of hazard, one called the structural hazard, the other one called the data hazard, and the third one called the control hazard. We will go through each one of them with some example. The structural hazard is the easiest one, and we will just see one slide on that. This happens because two or more instructions require the same stage of the pipeline at the same time. Okay, let's give an example. Supposing, let's say, the ith instruction is a load instruction, and the I+2nd instruction is any other instruction, and let's assume that my processor has a single memory port. Then the ith instruction, which is a load instruction, goes through the pipeline. Then in the next cycle, the I+1th instruction is being fetched, and in the subsequent cycle, the I+2nd instruction is being fetched. Now you can see that by the time the I+3rd instruction goes to the instruction fetch stage, the ith instruction would already be in the mem stage. If both of these instructions, that is the ith instruction as well as the I plus third instruction, are going to access the memory, and there is only one memory port which is available, then both of them would contend for that memory port, right? And only one of them should be allowed to execute, and this is essentially what is called a structural hazard. Let's say if the ith instruction is allowed to proceed forward, then the I plus 1th instruction is going to be stalled, and therefore in this cycle, right, the I plus third instruction could not be fetched, and that instruction has to be only fetched in the next cycle. And because nothing was fetched in this cycle, there is going to be one bubble after this write back, right? And in that cycle, we are not going to complete any other instruction. Okay, the simplest way to solve the structural hazard is to increase the number of resources, or in this case, increase the number of memory ports. Okay. All right. So let's now talk about data dependencies and hazards due to data dependencies. For that, first we need to understand the types of data dependencies in instruction execution, right? First, we will talk about true dependence, or what is called the read after write dependence. And let's just take this particular example, right, of instruction sequence, where the first instruction copies some value from the R7 register into R3, and then the second instruction essentially uses that value of R3 to perform a load operation, and the third instruction computes something to R3 and then stores the value back into R3. So in this case, the second instruction is dependent on the first instruction, or the second instruction has to read the value produced by the first instruction, and that dependency is what is called the read after write dependency, because this read of the source operand has to happen after this write has happened, right? That is why it is called the read after write dependency. As opposed to this, there is a dependence from the second instruction to the third instruction, right? The second instruction has to read the value, right, for performing this operation before the third instruction can overwrite into it, because if the third instruction overwrites into R3 register before the second instruction can read the value for performing the load, then of course you would actually fetch the wrong value for the load, because the address would have been changed. Therefore, this dependence that you see between the second and third instruction is what is called the anti-dependence, or write after read dependence, right? The third dependency is between the first instruction and the third instruction, both of which write to the same register R3, right? And in this case, you want the first instruction to complete its write before the third instruction can write into it, because if they are written in the other order, then the subsequent instructions which are reading the value of R3 would read the wrong value. They would not read this value of R3, but they would end up reading that particular value of R3, which is not what is intended by the programmer. So this dependency is essentially what is called as the write after write dependency, or WAR dependency. Okay, so when you are doing instruction execution, it is important that all of these dependencies have to be obeyed. The true dependency happens because of the values produced by one instruction has to be passed to the other instructions, whereas the other two dependencies, anti and output dependencies, happen more because of the fact that you are reusing some of the registers. If this instruction has used, let us say, some other register instead of R3, for example, if you have used an R13 register here, then this WAR dependency would not have been there. And similarly, if this had been R13, this WAR dependency also would not be there, right? Therefore, these two dependencies are also called the false dependencies, whereas this is called the true dependence, right? Now, you can see that this dependence cannot be changed by renaming this register to something else, because if I rename this to R13, then that is not essentially same as what was originally in the program. If I rename this to R13, then I have to rename this also to R13. If I keep this as R3, this has to be R3 in order for me to preserve the semantics of this program. Therefore, true dependencies, right, are important from the perspective that they have to be always preserved. Anti and output dependencies, right, can be overcome or can be eliminated by renaming the registers. Okay, now let's look at the data hazard part of it. Okay, here is an example. Let's assume that the ith instruction, right, produces a value which is in R3 register, and the I plus 1th instruction uses this value of R3. In the case of non-pipelined execution, the ith instruction would go through all the stages, complete the value, write the value into R3 register, and then the I plus 1th instruction can read from it. Whereas in the case of a pipelined execution, you can see that the I plus 1th instruction is trying to do the operand fetch during the instruction decode stage. So it's trying to read the value from R3 register in this stage, which is time step 2. If the value of R3 written, if the new value of R3, which is the addition of R1 plus R2, written in R3 at this particular time step, the answer is no, because this instruction would write the value in the destination register only in time step 4. Whereas this instruction is trying to read that value from that register in time step 2, which is not possible, right? So this cannot be done. Therefore, the I plus 1th instruction has to be stalled. It has to be stalled not just in that cycle, but also in the next cycle, right? Because even then the value would not be ready, because you are trying to read it in time step 3, whereas it will only be written in time step 4, right? Perhaps in the next cycle, right, the I plus 1th instruction can go for execution if the value is written, let us say, somewhat in the initial part of the cycle, and you are trying to read it in the later part of the same cycle. So because of this true dependence between the add and subtract instruction, right, the pipeline has to be stalled, and it has to be stalled in this particular case for 2 cycles before its instruction, right, there before the I plus 1th instruction can go to the instruction decode stage and execute. This is essentially what is called the hazard that has happened because of the true data dependence, and this is why it is called the data hazard, right, because of the dependence that has happened, that is there in the program. Okay, now let's see whether we could have done something smarter to avoid these 2 stalls, right? Okay, this is what is called as the pipeline interlocking or pipeline forwarding. Let's look at the example and then see how it can be implemented. Okay, again we are going to take the same example, the ith instruction being an add instruction, and the I plus 1th instruction is dependent on this add instruction. Even though the ith instruction is going to write the value in the destination register only in the write back stage, we know that the add instruction is actually going to produce that value, which is the addition of R1 plus R2, right at the end of the EX stage, because at the end of the EX stage, you would have actually computed the arithmetic operations value, right, which was there in the ALU out temporary register, and it is only written in the destination register in the write back stage. So technically speaking, the value is available at this point in time, but it is not available in the R3 register, which is the destination register. So the question is whether we should read the value only from the R3 register, or can we take the value from the ALU out, right? So if you allow the instruction execution to take the value from the ALU out, then what we can do is that we can actually forward the value from the ALU out to the EX stage of the I plus 1th instruction, and therefore the I plus 1th instruction can actually go ahead and compute the value, right? Similarly, if you are talking about an I plus 2nd instruction, which is also dependent on the ith instruction, then for that also, because in its ID stage, it cannot read the value from R3 because R3 is going to be only written at this cycle, correct? You also have to forward the value, right? But instead of forwarding this value from this particular buffer 1 cycle later, what we do is that we forward the value from the next buffer, right, in that particular cycle. Right, this is what you wanted to. You wanted to forward this value, but then you want to forward it not in cycle 3 but in cycle 4. But when you go to cycle 4, this value would have been copied from this buffer to this buffer. Therefore, you are forwarding it from that buffer to the EX stage. Right. So this is essentially what is called as pipeline forwarding, and pipeline forwarding is implemented by means of additional data paths and through a larger multiplexer. So earlier we only had A and NPC going into the multiplexer, but now you have all of these forwarded values from different places which also form as the input, and it could be either for the first source operand or it could be for the second source operand, and that's the reason why you have these additional values floating up. Okay. So it could be the same ALU out value going from this cycle, or it's the same ALU out value going through this green arc which is being shown here. The black arc essentially is taking the value from the load instruction or the LMD register, and it is forwarding it to the subsequent instructions. Okay. Okay, now I said about load instruction, but load instruction presents one little challenge. Let's see what that is. Okay, if the ith instruction is a load instruction and the I+1th instruction is a dependent instruction, the ith instruction produces the value in R3, which is what is going to be read by the I+1th instruction. Now let's see whether we can do forwarding and then execute this instruction, right? So again, we will assume that during the ID stage, you can't read the value of R3 because R3 is not going to be available in R3 register. In fact, the value which is loaded from memory is going to be only available at the end of the cycle 3, right? It's only after the Mem stage the value is going to be available because it's a load instruction. At the end of the EX stage, you only have the effective address being calculated. Only at the end of the Mem stage, you have the value loaded from memory. So the question is, can I forward the value from here, which is at the end of cycle 3, to the EX stage at the beginning of cycle 3, right? This is what you want. That cannot be done. We cannot forward values in time, right? I mean, ahead of time. So this is not possible, and therefore this instruction has to be stalled, right? Even if you allow pipeline forwarding, it cannot forward because it's only available after the Mem stage, right? So the only way by which this instruction can be executed is one cycle later, right? And again, you are doing a forwarding from the Mem stage directly to the EX stage. The value is going to be written only after this, but you are forwarding the value from that particular buffer to the EX stage, right? So in case of a load instruction, and if the next instruction is dependent on the load, then it has to be delayed at least by one cycle. Okay, this also holds for other instructions or operations which take multiple cycles to execute or multiple cycles in the EX stage to complete. They will require a fewer stall cycles to implement, even if you have pipeline forwarding. Okay. So that's essentially what it says. Forwarding cannot eliminate all stalls, particularly in deep pipelines. In deep pipelines where the EX takes multiple stages, right? Then if EX takes, for example, let's say 3 stages, then you can only forward after 2 instructions. Not, that is, if the ith instruction and the I+3rd instructions are dependent, then that dependency can be resolved by doing forwarding. But if the ith instruction and the I+1th instruction are dependent, then you have to incur 2 stalls. If the ith instruction and the I+2nd instructions are dependent, then you have to incur 1 stall cycle and so on. Okay. So the pipeline has hardware mechanisms which will detect these dependencies, and then depending on whether the dependencies can be resolved using pipeline forwarding or not, right, it will allow the instruction execution to go, or it will stall the pipeline. Okay, let me spend the next 5 minutes or so talking about control hazards, and then again take let me skip this slide because this talks about instruction scheduling, which is more interesting from a compiler perspective. But let's just skip that slide. Let's just go to the last hazard, which is the control hazard, right? And then see what happens in the case of branch instructions. Supposing, let's say that the ith instruction is a branch instruction, a conditional branch instruction, right? Then we know that in the case of a conditional branch instruction, the condition is evaluated at the end of the EX stage, and the target location is also calculated only in the EX stage. Now, right, the EX stage is the third stage in the pipeline, or this, right? Now, what happens after the ith instruction is fetched, right? In the next cycle, you want to fetch the instruction. Now, that the previous instruction was a branch instruction, and you don't even know whether the previous instruction has to do a conditional branch or not. And even if you know that it has to branch, you don't know where to branch to, right? Because all of that is going to be calculated only in, let's say, cycle 2. Whereas in cycle 1, you have to fetch the next appropriate instruction, right? Therefore, if the ith instruction is a branch instruction, then in the next cycle, we don't even know what to do. So we have to incur a stall there, right? And we also have to incur a stall in the subsequent cycle until we compute the branch target address over here, and until we compute the conditional, right, whether the branch is going to be take place or not. So once you know that information, then in the next cycle you can actually fetch instruction either from the I+1th location or from the target location, depending on whether the condition is false or true, right? So in the case of in the case of branch instructions, conditional or unconditional, right, because you have to jump to a different location, in the next cycle you can't actually fetch instructions, right? So this also adds additional stalls to your pipeline. This is what is called as the control hazards, right? Of course, some amount of control hazard can be aggressively addressed by doing certain calculations in the instruction decode stage itself. For example, here you can actually calculate the target location calculation. You can prepone that from the execute stage to a prior stage. You can also calculate whether this register value is greater than 0, less than 0, because that comparison doesn't really take a long time. So in some sense, you can actually move the target address calculation plus the condition evaluation to the instruction decode stage, but still you will incur one stall cycle, right? Because at least it takes one cycle to fetch the instruction, and then the next cycle you can decode and execute the instruction as much as possible so that, right, it can be executed in 2 cycles. But even then, right, in cycle 1, you don't know whether to fetch from the I+1th instruction or from the target location. So you have to stall or pause for 1 cycle, and then only in the next cycle you can fetch and execute the next correct instruction, right? Okay, so that's essentially what is a control hazard. And one simple solution for control hazard is to pretend, right, that the ith instruction is not a branch instruction, or ith instruction, even if it is a branch instruction, it is not going to take the control branch. This kind of a prediction is what is called as the static branch prediction policy, and you are basically predicting the branch to be not taken. What is the advantage? The advantage is that if you predict the branch to be not taken, then the next instruction that you have to fetch is the I+1th instruction, for which you already have the program counter, so you can actually go ahead and fetch the instruction. But if it so happens that after that cycle you find out that the branch is indeed taken, then whatever instruction that you have fetched from I+1th location, just discard it, and then in the next cycle fetch the instruction from the appropriate location, right? So this is what is called as the static not taken branch prediction policy. And if the prediction is correct, then you don't incur the stall, because you have already fetched the instruction from the I+1 location, and you can actually go and do the decode in the next cycle and so on. But if the prediction is wrong, then that instruction has to be squashed and you are anyway wasted one cycle. But even if you have not done the prediction, you would have wasted that cycle, because for a control hazard, you have to definitely incur one stall cycle. So this is why the not taken policy is very useful, right? Whenever the branch is not taken, you save the wasted stall cycle, but whenever the branch is taken, you anyway have to incur that stall cycle, and you incur it. There is also a mechanism called delayed branching, which is often implemented. And the way delayed branching works is that typically you say that the instruction following the branch is always executed in the next cycle, and the branch takes place only after that cycle, right? And one can always fill the instruction following the branch with a no-op instruction, because executing a no-op instruction doesn't change anything. And therefore, if the ith instruction is a branch instruction, the I+1 instruction can be fetched and executed. Then the control transfer takes place only from the cycle after that, right? That's the default way of executing. By this, you are not really achieving anything except that the instruction following the branch instruction, which is a no-op instruction, also gets executed. But there is no additional benefit, because instead of wasting a cycle, you are executing a no-op instruction. But the real benefit comes if you can actually move some useful instruction ahead of the branch into the location where the no-op is. So for example, if you call this as a delay slot, and then if you can actually move the add instruction on which the branch is not dependent on into that location, then the ith instruction would be a branch instruction, and the I+1 instruction, which is an add instruction, which should have been executed even before the branch instruction, would actually be executed after the branch instruction, irrespective of whether the branch condition is true or false, right? So thereby you will save that delay slot. So this is essentially what is called as the delayed branching. Most of the RISC processors do implement this kind of a delayed branching. There are also additional details about delayed branching, but we will not get there due to lack of time. Okay, so I think what I will do is I will again pause for a few minutes for questions from you before I go to more complex branch prediction policies. Are there any questions?
Hello, sir.
Yeah, go ahead.
So, could you go back to the slides pertaining to forwarding?
Okay.
Yeah. So, here when you talk about the buffers, right? So okay, it's more of a problem where I don't see it being efficient in terms of register allocation, or in terms of, okay, so the like I don't see how it is possible for us to have enough registers to keep track of all the registers, given
So when you
that
say we, you're talking about the compiler or the assembly language programmer?
Okay, so yeah, that is actually where my question comes from. So what kind of
these are all temporary registers which the compiler or the assembly language programmer is not going to see. These are all internal registers. You don't have access to them at all.
So where do they come from? Like
they are in the hardware, and the hardware uses them for their purposes.
So assembly programmer or even a backend writer does not have to care about pipeline when he's writing the compiler.
I don't say he does not have to care about. He needs to know about them, but then he cannot directly access the A register or the B register, or these registers which are in between these buffers.
Okay,
right?
So
but if he knows that pipeline forwarding is implemented, then he can put the ith instruction and the I+1 instructions as dependent instruction, and he doesn't have to worry about it. Right? But he doesn't have to worry about in which register, from which register it is going to do the forwarding, because that's internal. Hardware will manage that.
Okay. So depending on the depth of my pipeline, I mean depth of the pipeline, the processor will have enough registers to take care of the worst case possibility.
Again, you are confusing the general purpose registers which we normally talk about, which is what is exposed to this. So I said in the case of MIPS, there are 32 integer registers and 32 floating point registers, which is what is exposed to the programmer or the compiler writer. You always worry about them.
Okay.
Correct?
Yeah.
In addition to that, there are several other registers which are not exposed to the software, which the hardware manages by itself. Right? Don't worry about them.
Right.
That's for the hardware to worry about.
Right. Okay.
Okay.
Yeah. Then it makes sense.
Yeah.
So
Any
you
other
mentioned,
questions? Yeah.
so you mentioned that some of the things are managed by hardware. So I think you are trying to say is that the difference between ISA and micro architecture details associate. I mean
Correct.
that are
Those are actually micro architectural details. Yes.
Yeah. So can you put on some let's say comment on the trade-offs between the exposure of these things to the, let's say, compiler writer or to the general purpose programming? So what
Some
should
of
be
the
hidden in?
Okay, so let's not even talk about trade-off here because I don't know whether it's an appropriate way of looking at it.
Okay.
Right? Some of these, no, don't take okay as an answer. The reason that I'm trying to say is that some of these hardware things, like for example, the registers in these buffers, right? It's not even a good idea to expose them to the compiler writer because he's not going to manage them, right? And it has to be only managed by the hardware. So there is no question of a trade-off that is coming into picture here, right? So there are other cases where you talk about the trade-off, but definitely not here because there are certain things which has to be kept within the hardware, and these internal registers are pretty much the hardware things. Like these are hardware states, let's say, right, which need not have to be exposed to the compiler writer or the assembly language program.
Okay. You meant kind of these are kind of micro instructions kind of state that are not exposed.
Instructions or micro architectural details per se.
Not exposed to programmer.
Yeah.
Okay.
Yeah. Right.
Thank you.
Yeah. Sorry if this is too naive, but okay. So we I mean, take the example of this the register that you gave here, right? The value is written after EX. I mean, EX is done to the temporary register that is a part of the hardware, but it's actually written to the GPR only after the write back.
Only in the write back stage.
Yeah, exactly. So I mean, again, this is where the naive part comes in. So why? What is the? I mean, this is. I think.
Why can't we write it right here itself?
Exactly. I mean, why can't we? If we had access to the the hardware registers, like
you don't have access to it. The hardware has to do it. Okay. The question is, you want to do the things in some particular way, let's put it like in an organized way, right? So you have this notion of a write back stage where you want to do the write back, right? If you want to fold this write back, whatever you are trying to do here, right over this stage itself, then you are going to extend the EX stage, right? Which might extend your cycle time, which might make other complications, right? And you have done it in such a way that whether it is an arithmetic instruction or a load instruction, write back happens appropriately. Now you are taking some parts of it and putting it over here. Then for load instruction, you have to take some parts of it and putting it over here. Then you're going to stretch different things differently, and you're going to manage the hardware, which makes things a lot more complex, right? So those are issues that we may not have a lot of time to talk about, but there are issues that are there.
Yeah, but I think this is where the question about control and trade-off comes. I mean, even makes sense. Like
no, you don't want all of this to be managed by software. Believe me, no compiler or no software programmer is going to manage all of these things. Want to manage all of these things, right? Okay. How many of you know about the number of registers that are being used in your C program? We don't even look at it, right? When you write your C code, You don't even know whether it is using 32 registers or 16 registers or 64 registers, right? These are general purpose registers which are exposed to the compiler assembly language programmer, right? We don't look at them. Now you are saying that I want to look into these micro architectural registers and storage spaces.
No, not as a usual as a normal programmer, as a compiler engineer maybe.
Even as a compiler writer, you don't want to. You want to restrict yourself to the general purpose registers and be done. You may not have control on them, right? They are not exposed to the software, and B, you don't want to manage that kind of a complexity. And that's the reason why it was not exposed to the software.
Right.
Okay.
Yeah.
So let's move forward because I have several other things to cover, right? And we will spend more time. We'll probably eat into your break time also, right? Sorry about that, but I have too many things to cover, I believe. Okay, so let me just go forward and then very quickly talk about dynamic branch prediction. So static branch prediction is actually a very naive technique where you simply pretend that the branch is not taken and fetch the next instruction. That may not necessarily be enough to address, because in your program, typically every fifth instruction or sixth instruction is a branch instruction. And roughly about 50 to 60% of the branches are taken. So a static not taken policy is not going to be very effective. So there are several other branch prediction policies that were or branch prediction schemes that were invented. So let's just talk about simply the simplest one of them, which is the one-bit branch predictor. The one-bit branch predictor essentially looks at all the branches, or looks at each of the branch as and when it is encountered, and then stores the history of what happened in the previous time when the same branch was executed. So if the last time when the branch was executed, if it is taken, then that information is stored. If it is not taken, then a 0 is stored to indicate that it was not taken. So the next time around when you encounter the same branch instruction, you look back into this history and then use that history information and then say that, look, based on what has happened in the past, now let's predict this branch is not taken, or let's predict this branch is taken, and then see whether that prediction is correct or not. Again, if the prediction is correct, you save the stall cycles. But if the prediction is wrong, you have to squash those instructions which were speculatively executed and then restart the execution from the current path. Okay, so how does the predictor work like? So you essentially have a set of entries in a table where each one of this entry would correspond to one static branch instruction, and what happened to that static branch instruction the last time when it was executed. So for example, let us say that there is a branch instruction in a program counter location PC, and the last time when that branch was executed, it was not taken. So the next time around when the same branch instruction is being fetched, the same program counter value is used, and then you index into this what is called the branch prediction buffer. You find that the bit to be 0, which means that the last time when this branch was executed, it was not taken. So you also predict this time also it won't be taken. If the prediction is correct, then you are good and everything is fine. If the prediction is wrong, of course, you have to squash that, right? In both cases, after the branch is resolved, whatever has happened, whether the branch is taken or not taken, that bit is again set in this, so that the next time around when you come to the same branch, you can again use this information for prediction, right? So that's essentially how a one-bit branch predictor works. Typically, the branch prediction buffer is something like 1024 entries or 2048 entries, and you index this branch prediction buffer using, let's say, either 10 bits or 11 bits of the program counter, right? So different static branch instructions would actually fall into different locations. It is possible that more than one branch instruction may be having the same number of, having the same 10 PC bits to be the same, in which case they will point to the same location, which is what is called as aliasing, right? So influence of one static branch might influence the other static branches because their program counter values are identical. Those 10 bits of them are identical. So they may point to the same location, but that's okay. That's only in some rare cases. Okay, right? You can improve this 1-bit branch predictor by what is called as a 2-bit branch predictor, because the 1-bit branch predictor is very flippy in the sense that if the last time the branch is taken, the next time you predict as taken. If the last time the branch is not taken, this time you predict as not taken. And for certain branches, which particularly in loops, right, it's often that you know, 90% or 95% of them time, or let's say that if it is, you know, an iteration for 100 loops, right, 100 iterations, then 99 times it is taken and once it is not taken, and again 99 times it is taken and once it is not taken. So if you have a 1-bit branch predictor, they may not really work well for them. So for that purpose, what you do is that you introduce what is called a 2-bit branch predictor, and you implement the way in which the 2-bit branch predictor works as a finite state machine, right? And in this finite state machine, because we are talking about 2 bits, there are 4 states, right? And one of the state is what is called the strongly taken state, in which the branch predictor is going to predict the outcome of the next branch for the same location as taken. And as long as the prediction is correct, it will continue to be in the same state. If the prediction is wrong, it will go from the strongly taken state to what is called as the weakly taken state. And even in the weakly taken state, the prediction is taken. That is why it is called weakly taken, right? The prediction is still taken, but it is a weak prediction, in the sense that you have predicted wrongly once, right? But if you again predict wrongly, then you go from the weakly taken state to a strongly not taken state. And in that particular state, you will predict as not taken. And as long as you are right in that state, as long as your prediction is correct, you continue to be in the same state. But if your prediction is wrong, then you go to what is called as a weakly not taken state. And again, even in the weakly not taken state, the prediction is not taken. But in the next time around, when the prediction is correct, you again move back to strongly not taken state. But if the prediction is wrong, you go to a strongly taken state. So it takes 2 wrong predictions to go from a predict taken to a predict not taken policy, right? Such kinds of branch predictors work much better for what are called loops. Okay, and typically the state transition diagram is implemented using a 2-bit counter, and as I mentioned earlier, they give much better accuracy in terms of doing the branch predictions. Okay, the 2-bit predictor essentially works well for nested loops, and here is an example which shows why it works better. For example, let us look at this nested loop, right? Let's say that the outer loop, right, is iterated 100 times and the inner loop is also iterated 100 times. Now, if you look at the branch prediction for the inner loop, right, the first time around maybe it's predicting as not taken. That's a wrong prediction. But then subsequently, it figures out that the loop has to be taken and it takes it for the next 99 times. The last time around, again, it will predict wrongly because at the 100th iteration, it has to break out of the loop and then come down, right? But the next time when you come back and then execute the same branch instruction, because it would have moved from a strongly taken to a weakly taken state, it will still predict as taken, and that prediction is correct, then it will again move to the strongly taken state and it will continue to predict correctly. So in the steady state, right, the 2-bit predictor would predict wrongly only once for every outer iteration, right, which is the last iteration of the innermost loop. And then the next time around, it will continue to predict correctly. So therefore, this predictor would have a 99% success or 99% correct prediction, as opposed to a 1-bit predictor, which would only have 98% correct prediction. Okay. So here again, you implement the branch prediction buffer by means of a table, which is again 1024 entries or 2048 entries. But here each location would contain 2 bits rather than 1 bit. Okay. And the bit values, like if it is 00 or 01, it indicates whether it is a not taken prediction. And if it is 10 and 11, it implies that it is a taken prediction, and so on. Okay. So let me just complete this branch target buffer and then stop, and then give you a time for questions and then also take a break. Okay. Now, so far what we have seen is that we have seen how to do the branch prediction, but we haven't really seen how to find out the target location. Remember that in the case of a conditional branch instruction, there are two tasks that has to be performed. One is to evaluate the condition. The other one is to evaluate the branch target location. Okay. So even if you predict as taken, if you don't know what is the target location, then it is not very useful, right? Therefore, to find out the target location, right, branch prediction schemes actually implement what is called a branch target buffer. Again, the branch target buffer is nothing but a table or a set of locations, and that stores the target address for different static branches which were seen. Okay. One nice thing about many of these direct branches is that the target location, which is essentially specified by means of a small constant, right, is always fixed. That means that for a particular program counter value, if there is a branch instruction, its target is always the same, irrespective of how many ever times it is being executed. Therefore, the first time when you execute a branch, you can actually calculate its target location, and then you can save the target location in the branch target buffer. The next time around when you execute the same branch instruction, you can use the program counter to index into the table and therefore find out the branch target location. Right? Now, if you think of all of these things, right, both the branch prediction buffer and the branch target buffers, right, they are always indexed using the program counter. Right? And if you have seen a branch the last time, then you would have updated the branch prediction buffer, you would have stored that value in the branch target buffer. So the next time when you come around, during the instruction fetch phase, when you have the program counter value, if you actually index into the branch target buffer and if you index into the branch prediction buffer, if you find that those PC values have an associated entry in the branch target buffer or an associated entry in the branch prediction buffer, then it means that this instruction was a branch instruction, it was seen earlier and it was executed, and at that time you figured out that it was a branch instruction and you saved the branch target location in the branch target buffer, right? Therefore, if you think about it, during the instruction fetch phase, right, just using the program counter, if you can index into the branch target buffer, and if you find that there is an entry which has a target location, then means that for that particular PC is actually a conditional branch instruction, right? You don't even have to do the instruction decoding. You know it even at the time of the instruction fetch stage. And at the time of the instruction fetch stage, you can actually find out what could be the target location. And the branch prediction buffer could tell you whether this branch is going to be taken or not taken. Therefore, in the next cycle, you can actually do instruction fetch from the predicted location, whether it is a target location or the next instruction. This is how the branch prediction works. Okay. One small issue or one small detail here is that again the branch target buffer is a fixed set of locations. Maybe it is like 1024 locations or 2048 locations, and therefore certain number of bits from the program counters are going to be used to index into it. So for example, if this is 1024 entries, then 10 bits, 10 least significant bits from the program counters would be used to index into the branch target buffer. It's so possible that two different branches in my program, right, would be in two different program counter locations, but the least significant 10 bits that I'm, right, that I have indicated over here might be same for these two branches, which means that they might be indexing into the same location, but the target address might correspond to only one of them. So how do we distinguish between the two things, right? So we distinguish between those two things by storing what is called the tag, which is the remaining bits in the program counter in that location. So whenever you encounter this, whenever you come back to the same program counter value, you index into the location, you take the value of this tag which was saved last time and then compare it with the current program counter value most significant bits. If they match, then you say that this entry essentially corresponds to this particular PC and this target address corresponds to the same target location. Now with this, if you see that any time that you find a valid entry in the branch target buffer with the tags matching, then it means that this instruction was a branch instruction and it was seen some time ago and the target address was calculated and saved here. So you can actually identify branch instruction even during the instruction fetch phase itself, right? If you find the entries to be available in the branch target buffer. Okay, so using this, right, and using these 2-bit predictors, typically branch predictors would predict branches during the instruction fetch phase of that instruction itself, so that in the next cycle they can fetch instruction either from the target location or from the subsequent locations. Okay, I do have some more details on more complex branch predictors, but in the interest of time, I'm going to skip them. Okay, let's stop here. Thank you.